Think about how you learned to throw a basketball. Every miss gave your brain feedback, and with each attempt, your muscles adjusted automatically. Machine learning works through the same principle. When a system gets an answer wrong, the math traces that error backwards through every single connection. Each weight gets a tiny nudge. Multiply that by millions of examples, and something remarkable happens. The system develops genuine capability, not because anyone programmed the rules, but because the math found patterns no human could specify by hand. That is the intuition most tutorials skip over. It is how machines build understanding from failure. But there is a massive gap between building a model that works in a notebook and building a system that works in the real world. We call this the transition from theoretical capability to reliable, real-world deployment. Machine learning is broadly defined as the capacity of systems to learn from data to automate analytical tasks. It serves as the foundation for modern artificial intelligence. A consensus across sources emphasizes that deep learning, a subset utilizing artificial neural networks, often outperforms traditional shallow models in complex applications. Yet, despite the breadth of applications in science and engineering, there remains a need for clearer integration between theoretical algorithmic development and the servitization of artificial intelligence in business contexts. The collective literature illustrates a maturing field balancing statistical rigor with deep learning architectures, though the transition continues to present unresolved complexities. Here's the thing. 80% of machine learning projects stall after the proof of concept phase. They never reach production. We often blame the algorithm or the data quality, but the real culprit is usually what we call production debt. It is a collection of technical and operational issues that accumulate as a project moves from a lab environment to a live system. These debts compound over time until the project becomes too expensive or risky to maintain. To understand why this happens, we need to look at the three most common patterns that cause these failures. The first pattern is data drift. Imagine you train a model to predict winter sales for a retail store. You feed it data from December and January. The model learns the patterns perfectly. It predicts a spike in toy sales. But then you launch the model in June. The world has changed. People are buying swimsuits, not toys. The model is still looking for toy sales patterns. It has no idea the context has shifted. This is data drift. It happens because the statistical properties of the input data change over time. The training data represents a snapshot of the past, but the live data represents the present. When the two diverge significantly, the model becomes unreliable. It does not know it is out of date. It continues to make confident predictions that are completely wrong. This is why models need continuous monitoring. Without it, you are flying blind into a storm. Now consider this second pattern: feature store misalignment. This is a subtle but devastating issue. In the training phase, you calculate features. These are derived values like averages or sums that help the model understand the data. You might calculate a rolling average of user spending over the last 30 days. But when you deploy the model, the system serving predictions often calculates that same rolling average differently. Maybe it uses a different time window, or maybe it handles missing values differently. The training environment and the serving environment are no longer speaking the same language. It is like giving a chef a recipe that calls for salt, but the kitchen only has sugar. The chef follows the instructions, but the dish tastes wrong. The model sees data that looks different from what it was trained on. It creates a mismatch that degrades performance silently. Fixing this requires a robust feature store that guarantees consistency between training and serving. Finally, there is the failure of shadow deployment. This is when you run the new model alongside the old one in production to compare results. You do not use the new model to make decisions yet. You just log its predictions to see how it would have performed. The hope is that you can validate the new model without risking the business. But this process often fails because the logging infrastructure is not robust enough. Sometimes the shadow mode is turned off because it slows down the system. Sometimes the data is not logged correctly. You end up with a model that you never actually tested in a live environment. You assume it works because it works in the lab, but you never saw it struggle with real-time traffic spikes or network latency. You skipped the stress test. You assumed the simulation was enough. It was not. These three patterns combine to create a debt that is hard to pay off. You have a model that is drifting, inconsistent in its inputs, and untested in the wild. The team tries to patch it. They retrain the model. They fix the feature store. They add more logging. But the underlying architecture was not built for this. It was built for a proof of concept. It was built to show that the math works, not to show that the system is resilient. This is the gap between a niche specialized skill and a ubiquitous capability. The field has evolved from a purely theoretical discipline into a highly accessible ecosystem. Comprehensive, multi-week curricula and open-source toolkits like scikit-learn and TensorFlow have democratized entry for non-experts and scientists alike. But accessibility does not mean simplicity. It means more people are building models, and more people are encountering these production debt issues. There is a distinct and necessary convergence between deep theoretical mathematics and practical application. Successful learning paths require a dual focus on rigorous mathematical foundations and hands-on coding in Python. But we also need to focus on the operational side. The proliferation of open-source repositories and structured learning modules indicates a trend toward standardization in machine learning education, reducing the barrier to entry and accelerating the integration of machine learning into general scientific workflows. Yet, the transition from theoretical capability to reliable, real-world deployment continues to present unresolved complexities. We need to acknowledge that building a model is only the beginning. Maintaining it is the real work. So, what is the path forward? You have to treat production debt like financial debt. You cannot ignore it. You have to plan for it from the start. This means building feature stores that enforce consistency. It means setting up monitoring that alerts you when data drift occurs. It means running shadow deployments that are actually tested and not just logged. It means accepting that the model is a living system, not a static artifact. The proliferation of open-source repositories and structured learning modules indicates a trend toward standardization in machine learning education. But the integration into general scientific workflows requires a shift in mindset. You are not just an algorithm engineer. You are a system operator. The field is maturing. We are moving beyond the hype of artificial intelligence and into the reality of machine learning operations. We are learning that the hardest part is not the math. It is the deployment. It is the infrastructure. It is the continuous monitoring. If you are building a model, do not stop at the proof of concept. Think about the data drift. Think about the feature store. Think about the shadow deployment. These are the patterns that cause 80% of projects to stall. If you can solve them, you can move beyond the lab and into the real world. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.